This section is on linear functions and their properties. I'm just going to abbreviate that. So if you look at your notes at the top, you're going to see something you've seen many times before, but it's that definition again of a linear function. It says a function of the form f of x equals mx plus b is a linear function. Now I know you're used to seeing it as y equals mx plus b. All right, it's exactly the same thing. Remember, y and f of x represent the same thing, where m, of course, is the slope, and b is the number portion of the y-intercept without the zero. So you put the zero in to make it a point. The domain is the set, so let's do the domain. It's the set of all real numbers. And the range is the same thing. So if you look at the top again of your notes, you'll see right below that definition it says average rate of change of linear functions. And the theorem says that linear functions have a constant average rate of change. In other words, the line is growing at the same rate over the entire course of that line. So the average rate of change of a linear function, that is f of x equals mx plus b, is just this. The change in y over the change in x. Well, that should look very, very familiar to you because that's just another way to say slope. So average rate of change is the same thing in a linear function as slope. And that's what you kind of need to know here. So let's look at example 1. We have a graph, f of x equals negative 3x plus 7, and this is kind of old stuff. So if I did an f of x table, or xy as you see in your notes, same thing, and I pick some points, I'm going to show you how the average rate of change, or the slope, is constant. So let's pick some points. If I put a 0 in for the x, that would just be a 0 here, so that would go away, and I would get 7 for f of x or y. If I put a 1 in for x, I would have f of 1 is equal to negative 3 times 1 plus 7, or f of 1 is equal to negative 3 plus 7, which is 4. If I put in 2, I would have f of 2 is equal to negative 3 times 2 plus 7, or f of 2 is equal to negative 6 plus 7, so that's just 1. Let's put in a 3 as our final point. F of 3 would be equal to negative 3, take out the x, put in a 3, plus 7, or f of 3 is equal to negative 9 plus 7, which is negative 2. And I've got a set of points here. Now what we're going to do is we're going to take them two at a time. So I'm going to start with these two, the points 0, 7 and 1, 4. And I'm going to show you the slope for that set of points. So x1, y1, x2, y2, and I have the slope for those points would be 4 minus 7 over 1 minus 0, which is negative 3 over 1, or negative 3. Now let's take the next 2 points, these 2 points, and I've got the points 1, 4 and 2, 1, and I'm going to show you that the slope is again negative 3. So we would have x1, y1, x2, y2, so the slope would be equal to 1 minus 4 over 2 minus 1, or negative 3 over 1, which is once again negative 3. So the slopes are the same, and that would continue if I took the next 2 points, these last two. 2, 1 and 3, negative 2. I'm not going to actually do it, but you could do it. So the slope, or the average rate of change, is constant in this linear function. It's exactly the same no matter which 2 points you pick. I could pick this point, and I'm still going to get a slope of negative 3. So it has a constant average rate of change. So when we graph our function, and I graph the points 0, 7, I'm just going to put that up here, 1, 4, be about here, 2, 1, and my graph isn't done correctly because I didn't really line these off. But you can see that it's linear. It makes a line, and no matter where you go on the graph between any 2 points, that slope is exactly the same. So that's what it means when it talks about the average rate of change. Just know it's another way to say slope. All right, let's look at an application of a linear function and some of the properties of that application. So we look at example 2, and it says book value is the value of an asset that a company uses to create its balance sheet. Some companies depreciate their assets using straight line depreciation, meaning it goes down the same amount each year, so that the value of the asset declines by a fixed amount each year. The amount of the decline depends on the useful life that the company places on the asset. Suppose that a company just purchased a fleet of new cars for its sales force at a cost of $28,000 per car. The company chooses to depreciate each vehicle using the straight line method over 7 years. This means that each car will depreciate by, now think about it, its original value is $28,000. Divide that by the years they're going to keep it, and it's going to go down, we're going to say, by $4,000 per year. So in 2a it says write a linear function that expresses the book value v of each car as a function of its age x. So we would say v of x, that's what it means, value as a function of x, is equal to, well, it's going down 4,000 per year. So as an integer, that would be negative 4,000. So we've got negative $4,000 per year, meaning times the number of years, plus the $28,000 that it starts at. So think of this a different way. It starts at $28,000, and then every year it goes down 4,000. So at 0 years, it's worth $28,000. At 1 year, it's 4,000 times 1, subtracted from the $28,000, etc. Well, this represents the slope, m, because it's in y equals mx plus b form, and this represents the initial value, or what we call the y-intercept. This is my b. So you need to recognize this is y equals mx plus b. All right, let's look at b. It says graph the function. Mine isn't going to be very accurate, but we're going to do this. It starts at a value of 28,000 at year 0. That's one car. All right, so we've got our years here and our value there, v of x. At 1 year, it drops by 4,000. At 2 years, it drops another 4,000 right there. At 3 years, another, and it keeps going down until it's valued at 0 at 7 years. Now again, mine is not done to scale, but on yours you can do that. If you label your horizontal axis in years, 1, 2, 3, 4, 5, 6, 7, and then you show the values here going up by 4,000. Now, if you didn't get that, you could create an f of x table, and we could fill that in. So at 0, it's really v of x, excuse me, not f of x. We would have v of 0 equals negative 4,000 times 0 plus 28,000. That goes away, and you've got 28,000. At 1 year, you would have v of 1 equals negative 4,000 times 1 plus 28,000, which is 24,000, etc. And that's going to give you your points. C, it says, what is the book value of each car after 3 years? In other words, what is v of 3? So that would be negative 4,000 times 3 plus the original initial value of 28,000, or v of 3 is equal to negative 12,000 plus 28,000. So v of 3 is equal to 16,000, the value after 3 years. All right, let's look at D. It says interpret the slope. In other words, what is it meaning? The average rate of change means that the value of the car decreases by $4,000 every year. And how do I know it's a decrease? Because the slope is equal to negative 4,000. Remember, it was negative 4,000x. E, when will the book value of each car be at 8,000? Now that's not. Now that's a little different than when we did B or C, and we were looking for V of 3. Now we want to know, when does negative 4,000x plus 28,000, when does that equal 8,000? Well, we can solve that equation easily for x, which remember is the number of years. So I'm going to subtract a 28,000 from both sides, and we end up with negative 20,000 equals negative 4,000x. Divide by negative 4,000, and you get x is equal to 5 years. So in 5 years, going down at 4,000 per year, the car will be worth 8,000. All right, finally, let's look at example 3. It says the quantity supplied of a good is the amount of a product that a company is willing to make available for sale at a given price. So that's quantity supplied. The quantity demanded of the good is the amount of the product that the consumers are willing to purchase at a given price. Suppose that the quantity supplied, we're going to call that S, and the quantity demanded, D, of cellular telephones each month are given by these functions. So the quantity supplied is a function of its price, so supply as a function of price is equal to 60p minus 900. And then we have the quantity demanded, so the amount demand as a function of its price is equal to negative 15p plus 2,850. So those are the two equations. P is the price of the phone in dollars. So let's look at A. It says the equilibrium price of the product is defined as the price at which the quantity supplied equals the quantity demanded. So however many they make, they sell them all because the price is right. That's called an equilibrium price. And so the equilibrium price is the price where S of P, the amount supplied, is equal to D of P, the amount demanded. Find the equilibrium price of the cellular telephones. And then we'll come to the next question. So that's really saying, when does S of P equal D of P? So all we have to do is take these two equations and set them equal to each other and then solve for P to see at what price is that true. So we're going to say 60p minus 900, that's the S of P, equals negative 15p plus 2850. That is the D of P. And now we're just going to solve that. So let's add a 15p to both sides. We get 75p minus 900 equals 2850. Add our 900 to both sides, and we get 75p equals 3750. Divide both sides by P and 75, and we get P equals $50. Now what does that mean? It means that at $50 per phone, they will sell the same number of phones that they have supplied. They will sell them all. There'll be no leftovers in the warehouse. Okay? Now the next question says, what is that amount that they will sell, given that we know the price that's going to work? What is the equilibrium quantity, the amount demanded or supplied at the equilibrium price? So what we need to know is, since we just figured out the price where S of P equals D of P, we can either solve for S of P or D of P. Either one, it doesn't matter because it's going to be the same. So let's do S of P. We know that P is 50, so S of 50, and we're going to go back to our equation, equals 60 times our 50 that we found minus 900, or 3,000 minus 900, which is 2,100 phones. All right, now just to prove the point, let me now find D of P, with P being 50. that would be equal to, go back to your D equation, negative 15 times 50 plus 2850, or D of 50 is equal to negative 750 plus 2850, which is also equal to 2100 phones, as it should have been, because that's the price that we discovered right here is going to let supply equal demand, no phones left over. So the conclusion here is that at $50 per phone, this company will sell 2,100 phones, and I think it was per month. That's a 21, by the way, per month, and they will have no surplus. They will all sell because people will be willing to buy them at that price. All right, let's look at B. It says determine the prices for which quantity supplied is greater than quantity demanded. In other words, at what price will the supply be greater than the demand? Now think about that. If at $50 per phone they sell every phone they make, then to have leftovers, it's probably because the price is too high, right? Not because the price is too low. So we're looking for where the supply is greater than the demand. Well, that's fairly simple. We can fill in our supply equation, and we just want to know when is that greater than the demand. And we've already solved it as an equation, so we know it's going to be when the price is greater than 50. And if you continue to solve this inequality, you will see that if they charge more than $50, then they're going to have leftover phones, because the quantity supplied will exceed what's demanded, and there'll be excess phones in their inventory. So that's what that means. And you need to be able to do a problem like this and draw the conclusion of what does that mean. Finally, in C, it says graph S equals S of P. Oops, I don't know why I put that. And D equals D of P, and label the equilibrium price. All right, now we're going to do this on 2 pages here. So let's go the price first, and then we're going to do S of P, and then we're going to do the price and D of P, and then we're going to do them on the same coordinate plane, and you'll see what happens. So if the price was 0, if I put a 0 into that supply equation, which was S, now we want of 0 equals 60 times 0 minus 900, we would get negative 900. That doesn't even make sense. If I put a 0 in here, which is going to be my x-intercept, I would have S of P, because I don't know what it's going to be, equals 60 times of P minus 900. Let me rewrite that. I didn't say that right. We set it equal to 0, and I have 60p minus 900, so I add a 900 to both sides, and we get 60p equals 900, divide by 60, and you would get that p equals 15, meaning if the price was $15, what the supply would be. We can continue to put in some points. You can do this on your calculator. I'm just going to fill this in on what you get when you put values in for P. We already know this one because this is the equilibrium. Now if I go over here and I do the same thing with the D equation, going back up here to your D equation, I have these points. Again, I'm going to let you do that on your calculator, picking numbers for P. We get 2550. If we have 50, again, we know. Now notice, that point is the same, so we already know that's going to be where the graphs cross. So if you now, on your coordinate grid that is there, which is just an enlarged quadrant 1, if I put the price here, and then I'm going to do 2 graphs, I'm going to do S of P, the supply, what's supplied, and then D of P on the same graph. And this is how I labeled mine. 0, 1, 2, 3, 4, 5, 50, 1, 2, 3, 4, 5, and $100. So 10, 20, 30, 40, 50. And then here, I did them in increments of 500. So I've got 500, 1,000, 1,500, 2,000, 2,500, and 3,000. So now if we graph, and I won't be able to show you two colors because I don't have two colors of ink in my pen, but if I show you the two graphs, let's first do S of P. So I've got the point 0, negative 900, so that's off our graph, obviously. I have the point 15, which is right here, and 0. I have the point 30, so 10, 20, 30, 900, so that's almost here. And I have the point 50, 500, 1,000, 1,500, 2,000, 2,100. So that graph looks like this. And that is our S of P. Now if I graph D of P, the demand, if the price was 0, you can bet there'd be a lot of demand, wouldn't there? All right, that's 28.50. And then I have at 20, we have 25.50. If we only charge $20 a phone, the demand's going to be very high. So 25.50. And then at $50 a phone, we already know the demand is there. And on that graph, this is D of P. You can see that this is our equilibrium point where the graphs cross.